In this video, we're going to be putting some of our kinematic equations to work. So we have a problem that reads a cannonball is fired straight into the air with an initial velocity of 20.0 meters per second. The first part of the question is, what is the maximum height that the cannonball reaches? So if we have a cannonball that's fired up at 20 meters per second, we know that because there is a force of gravity on this cannonball, which is going to point towards the Earth, and that force of gravity is going to cause this cannonball to accelerate downwards, that it's going to reach some maximum height, where at that maximum height it is actually motionless for an instant, and then it's going to come back down. So our initial velocity in this case is 20.0 meters per second. I've decided to call up positive. And again, we're looking for the maximum height, so we know that at the maximum height, it has to come to rest for just an instant. That means the final velocity, in this case, is 0 meters per second. Our acceleration is just going to be the acceleration due to gravity, which is going to be negative 9.81 meters per second squared. Now, keep in mind, because I decided to call up positive, the direction of the acceleration needed to be negative because it's down. Okay? And again, we're just looking for the maximum height that we reach. Now we know that when I throw this ball up, or rather when the cannonball is fired up, it is going to come back down. It's going to hit the ground again. But what we did is we cut the whole problem in half. We cut the whole problem in half and we said it's going to go up. And right now that's all we're concerned about, when it goes up and reaches its maximum height. So it turns out there are two ways that we can solve this problem. One way that we can solve it is we can find the time, and we can find the average velocity. Another way we can solve it is we can go right to our kinematic equations that you're going to find right on your reference table, which relates all of these variables together. So if I rearrange this equation, because I'm solving for this displacement, I get Vf squared minus Vi squared over 2a. I plug in all of my knowns. 0 meters per second squared minus 20 meters per second squared, all divided by 2 times the acceleration due to gravity. You'll notice that it was very important I got my signs right, because it comes out now to a positive value of 20.4 meters for our maximum height. What would have happened if we calculated it a different way? Well, first we're going to find our average velocity, which we know is just our initial plus our final divided by 2. Plugging in our values, our average velocity is going to come out to 10 meters per second. Next, we're going to solve for the amount of time that it takes for the cannonball to reach the maximum height, and we're going to do that using this relationship. We know that an acceleration changes velocity over some time period. Okay? I know that this change in velocity is equal to negative 20 meters per second, because I started with a positive 20 meters per second and I ended at 0 meters per second. So rearranging the equation, I will simply solve for t, and I'll end up with 2.04 seconds. Finally, now that I have a time and an average velocity, I can use my relationship that says displacement, our change in displacement, will equal our average velocity times time. I plug in 10 meters per second for my average velocity, I multiply by a time of 2.04 seconds, and I end up with a change in displacement, or a maximum height of 20.4 meters. Okay, so now we're going to solve for part B. How long does it take the cannonball to return to its initial position? And again, I can separate this problem into two different ways of solving it. One is I can solve for 1/2 the trip, just going up, or I can solve for the whole trip. If I solve for half the trip, what I know is that it takes the same amount of time to come up as it does to come down. Alright, so our initial velocity again is 20 meters per second. Our final velocity is 0 meters per second because we're just taking how long it takes to get to the top. Our acceleration is negative 9.81 meters per second squared. And our time is currently unknown. So I grab my kinematic equations, and I find one that relates my final velocity to my initial velocity, acceleration, and time. I write it down. I rearrange the equation because I am interested in solving for time, and I plug in my values. 0 meters per second, because that's the velocity at the top, and I'm just dealing with half the trip right now. Minus 20 meters per second, all divided by negative 9.81 meters per second. And I'm going 9.81 meters per second squared, and I'm going to find a time of 2.04 seconds. Now, it's very important that I got the sign on all of these correct. It doesn't matter if I wanted to make up positive or negative, but it's very important that we recognize the acceleration is always towards the Earth. So in this case, it was opposite our initial velocity, because our initial velocity was away from the Earth. This 2.04 seconds was only how long it took to go up, which means I need to multiply it by 2 because I have to come back down. And the total time of flight would be 4.08 seconds. So now we're going to go ahead and solve this for the whole trip. Again, our initial velocity is 20 meters per second. Our final velocity, however, is negative 20 meters per second. This is because, if you remember, the speed at which something is fired up will be the speed at which it returns. Alright? The whole trip is symmetrical. The halfway point is right in the center. And so the velocity it leaves with will be equal in magnitude but opposite in direction to the velocity it has when it returns to its initial position. Our acceleration is still negative 9.81 meters per second squared, just the acceleration due to gravity. And I am just solving for time. I'm going to use the exact same equation from before, so I'm just going to go ahead and plug in my values. Negative 20 meters per second is my final velocity, minus a positive 20 meters per second, because it is the opposite direction, all divided by negative 9.81 meters per second squared. And again, I'm going to get a time of 4.08 seconds.